So given an equation in polar coordinates, it might be of the form r equals f of theta, or f of r theta equals 0, where f is some function of r and theta. The graph of the equation consists of all points P in the plane that have at least one polar representation r and theta which satisfies the equation. There are some things to note. The equation of a line through the origin is very simple. If the line makes an angle theta naught with the positive x-axis, then every point on that line has some polar representation r theta naught, so it satisfies the equation theta equals theta naught. Vice versa, any point satisfying the equation theta equals theta naught lies on this line. So the equation of that line is the simple equation theta equals this fixed angle theta naught. Now a circle of radius r naught, of fixed radius centered at the origin, has equation r equals r naught in polar coordinates. So for any point on this circle, the distance from the origin is r naught, so it has some polar representation where the r value is r naught, and vice versa, for any point with a polar representation where the r is r naught, it must lie on this circle. So for a circle centered at the origin, it has a very simple equation in polar coordinates, namely r equals r naught, where r naught is the radius of the circle. So if I want to graph the equation r equals 5, then this simply describes a circle of radius 5 centered at the origin. And if I want to graph the equation theta equals pi over 4, then this is simply the line through the origin making an angle of pi over 4 with the positive x-axis. And we've graphed both of them here in red. You see the line making the angle pi over 4 with the positive x-axis, and also the circle of radius 5 centered at the origin. Okay, so those are the simple graphs. Now suppose I'm given an equation of the form r equals 6 times sine theta, and I want to graph it, and perhaps I also want to convert the equation to an equation in Cartesian coordinates. The first thing I can do is what we all did when we started graphing functions. I can take a few values for theta and calculate the corresponding r's and plot the points and see if I can discern any pattern and join the dots. So the first thing I note about this equation is that r as a function of theta is periodic in theta. So if I take some angle theta and I look at the corresponding point on the graph, r is 6 times sine theta and theta is theta, it's going to be the same as the point r of theta plus 2 pi and theta plus 2 pi. So this graph will repeat itself as theta runs over the intervals of length 2 pi. So it's enough to graph this equation for values of theta between 0 and 2 pi. Now let's plot some points. So we take 6 angles between 0 and 2 pi. We take the angle 0, pi over 4, pi over 2, 3 pi over 4 pi, and then 5 pi over 4, 3 pi over 2. Those values of theta give us the corresponding values of r for the points on the graph. If theta is 0, the value of r is 0. If theta is pi over 4, the value of r is 6 times sine theta, which is 6 over the square root of 2. And if theta is pi over 2, the value of r is 6, etc., etc. So I get a sequence of points, and when theta is 0, the point on the curve is r equals 0, theta equals 0, so it's really just the origin of this plane. If theta is pi over 4, then the corresponding point on the graph lies on the line theta equals pi over 4 and is distance 6 over the square root of 2 from the origin. And when theta is pi over 2, the corresponding point must lie on the y-axis, and we have r is equal to 6, so it has a distance of 6 from the origin. So its Cartesian coordinates are given by 0, 6. When theta swings around to 3 pi over 4, once again the point is at a distance of r equals 6 over the square root of 2 from the origin, and when theta swings around to pi, we get back to a point where r is 0, which is at the origin, so we're right back to the point 0, 0 on the graph. And then if we increase the angle to 5 pi over 4, the r becomes negative, so the ray from the origin making an angle of 5 pi over 4 with the positive x-axis is in the third quadrant here, but because r is negative 6 over the square root of 2, this point coincides with the point for theta equals pi over 4. So it's in the first quadrant of a distance of 6 over the square root of 2 from the origin. So once again, it's repeating one of the previous points in the graph, and as theta swings around from pi to 2 pi, we get that this circle is traced out again. And of course, because this is a circle of radius 3 centered at 0, 3, we can easily write down its Cartesian coordinates. It's x minus 0 squared plus y minus 3 squared equals 9. Now it might be easier to plot the graph of this curve given by the equation r equals 6 times sine theta if you were to convert the points on the curve corresponding to the various values of theta to Cartesian coordinates. And of course, once you've figured out what the r is corresponding to a given value of theta, you can convert to Cartesian coordinates using the equation x equals r times cosine theta, y equals r times sine theta. So for example, when theta is pi over 4, you can calculate from your equation that r equals 6 times 1 over the square root of 2, which is 6 over the square root of 2. And if you want to convert that point r theta to Cartesian coordinates, x is 6 over the square root of 2 times cosine pi over 4, which is 6 over 2, which is 3, and y equals 6 over the square root of 2 times sine pi over 4, which is also 3. And in this way you might get a clearer picture of where these points are, and it might be a little easier to draw this graph. Here we have an animation of the graph of r equals 6 sine theta, and we see that as theta increases from 0 to pi, this equation traces out a circle sitting above the origin. And as the angle increases from pi to 2 pi, because the r is negative, this equation traces out the same circle again. So the full graph of this equation is simply the circle centered at the point 0, 3 with radius 3.